intermolecular forces. Stuff we've talked about before. So intermolecular forces. Now you've talked about intermolecular forces before. You've heard about intermolecular forces before. You've never, up to now, talked about where they come from, different types of intermolecular force, or anything like that. So we're going to make sure we know about those today. I would say it's relatively difficult because there's quite a lot of information to get through. So it is one of those things you're going to have to sort of study hard. If you've got questions, don't be afraid of the fact that the video going. I'll just pause the video and you can ask the question or whatever. So do wave at me if you've got any questions. Right. So what in this little lesson we'll talk about three, possibly a fourth type of intermolecular force. So we're going to talk about London forces. We'll talk about what we call dipole-dipole interactions. And we'll talk about hydrogen bonding. You've almost certainly heard of hydrogen bonding, but probably don't really know what it is, okay, or how to draw it properly so that we get marks for drawing it. And generally speaking, and you're expected to know that generally speaking, the strength of the intermolecular forces we'll talk about increases that way, so increasing strength. They get stronger as you go from London force to dipole-dipole to hydrogen bonding. We've got to be able to describe how these forces occur. We've got to be able to recognise when or what type of molecules exhibit these type of intermolecular forces, consider what effect that has on boiling point. Now, the one thing you should remember from GCSE is that intermolecular forces are, generally speaking, pretty weak. And so if you were to put covalent bonding on this continuum of strength, if you like, or this line here, covalent bonding would be way over here somewhere. You can't see my pen. It's way over to the right. So I'm not certain of the numbers, but I would say that covalent bonding is typically at least 10 times stronger than hydrogen bonding. Okay, so covalent bonds are very strong. These are all quite weak, but there are differences between them, and that's pretty important. Okay, so I'm going to go through these one at a time, but I am, when I finish, going to summarise by talking about something called van der Waals forces. So I'm going to make a note too, because you need to know the definition of van der Waals forces too. So make a note to yourself now to make sure that I do tell you what van der Waals forces are. Okay. Right. So let's go through these in turn. We'll go through them bit by bit, but I'll just remind you to start with what the word molecule means. Right. Molecule. The word molecule refers to simple covalent substances. So simple, M for simple, covalent. And typically speaking, that will be little groups of non-metals, right? So groups of non-metal atoms bonded together. You don't need me to tell you that. As we've been practicing drawing Lewis structures of these things like carbon dioxide, nitrogen, hydrogen, chlorine, water, all of that stuff, and methane, little groups of non-metal atoms joined together. Sorry, separate molecules, weak forces. And that means, of course, if they've got weak forces, they've got low boiling points. So all of the gases that we talk about, lots of things that are liquid at room temperature, almost certainly simple covalent, low boiling points, and they've got weak intermolecular forces, right? So that's the kind of GCSE level. Let's now crank it up and start talking about Key Stage 5 level intermolecular forces. We'll start off by talking about London forces. London forces, now all molecule types exhibit London forces. So all molecules have or show London forces between molecules. I always like it written to say between molecules. It's an idea that there's some sort of attraction between molecule A and its neighbour. They're not bonded together, but there is an attraction between them, which is why there might be a liquid at room temperature, or there might be a liquid if cold enough, or a solid if even colder than that. Okay, there's some sort of attraction between them, and all molecules have that. Even molecules that boil at ridiculously low boiling points, like nitrogen at -200 degrees, there are still weak intermolecular forces between them. Right, so this is what we call a sort of I'll say something else first. So even non-polar molecules. Another way of writing London forces, or describing London forces, is by saying that they are, and you should be aware of this, it's sometimes written like this in exams, it should be something like instantaneous dipole, induced dipole. I wish I could write induced dipole interactions. So that's meant to say interactions at the end there. Interactions is the last word. Instantaneous dipole, induced dipole interactions. And I'll explain what that means in a sec. What's up? Yes, the interactions at the end. The instantaneous dipole, induced dipole interactions. Sorry about that. I should say also that they're sometimes called London dispersion forces. So if you see it written in textbooks when you're reading, watching other videos, you've seen that too. Okay. So I'm gonna have a little bit of fun with you. I'm gonna pause the video and have a little bit of fun with you. Then we're gonna write it down as notes. So pause this. Do a little bit of demoing. So that was all very silly, but the whole idea was to remind you that if you've got a non-polar molecule, we've got an even distribution of electrons around that molecule, just like when you were dancing around the room there. And so you could imagine a non-polar molecule where the two atoms of, say, chlorine, or it might be a symmetrical molecule like carbon dioxide or methane or something, you've got even distribution of electrons around those two positive charges of the nuclei. So that molecule is non-polar on average. But at any one moment in time, those electrons could be unevenly distributed. Okay, so they could be, you could end up with what we call an instantaneous dipole. And it's still a non-polar molecule. This is just for a fraction of a second. Instantaneous dipole. Okay, so that molecule has become polarized. Now, which way is that polarity gone? Where's the delta negative? On the left of that molecule or on the right of that molecule? Can you shout left or right in 3, 2, 1? Left. Yeah, so we've got a very, very small, very temporary induced dipole on that molecule. Look like that. Okay, I'm going to flip over the page now and I'm going to draw that instantaneous dipole again. I need you probably to draw it again as well on the left of a page. There it is again. There's that instantaneous dipole. Instantaneous dipole. Right. So what that does is it can cause, the clue was in the name I mentioned earlier on, an induced dipole in a neighbouring molecule. So we've got a molecule with a little tiny bit of a dipole across it, tiny bit of a charge across it, if you like. And so a neighbouring molecule that might just be flying by, just be passing by because it's a gas, or maybe it's cooled down a bit, so it's turning into a liquid. Those electrons will be slightly pulled towards or attracted to that delta plus, right? And so this molecule has become polarized by the polarizing nature of the instantaneous dipole. And so we call this an induced dipole. Now, what you've then got is two molecules, both of which are ever so slightly polar for a short amount of time. And that means there's an attraction between the positive end of one of the molecules and the negative end of another. And that's what we call London forces. So you've been talking about these for years. We've talked about them. We've drawn pictures on the boards, dotted lines between molecules. That's one of the ways that they form, right? I'm going to pause the video while you just copy that up, and I'll take any questions. Okay, so you need to know quite a lot about London forces, I suppose. You need to know about the factors that affect the strength of London forces. So factors that affect strength of London forces. And there's a few things to consider. So the first of which you already know from GCSE in a way, which is the bigger the molecule, the stronger the London forces. But why would that be? So like decane with 10 carbons has got a higher boiling point than pentane with 5 carbons. But why? So it's all to do with the fact that the bigger the molecule, we get more electrons, so number of electrons. So for example, as you go down group 7, you go down from F2 to Cl2 to Br2 to I2, gas, liquid, solid, get increased MR, increased number of electrons, and then increased boiling point as a result. Simply because the molecules are bigger, right? They're all non-polar, and you know that from GCSE, but it's just tying it up a little bit more. Even the individual atoms, the noble gases, helium, neon, argon, krypton, xenon, even though they're not molecules, they have exactly the same thing going on. So the lowest boiling point substance, to my knowledge at least, is helium, which has got a boiling point of 4 Kelvin, which is minus 269 degrees C. So it's a very, very small atom. It's only got 2 electrons, but there's very, very, very weak interactions between them. But it boils at minus 269 degrees C. So there must be some sort of interaction between them when it's cold enough. Right. So number of electrons increases the strength of the London forces. Also, the size of the molecule, the physical size of the molecule, because the bigger the molecule, the more easily those electrons are polarized. So we had this picture up here of the electrons in the second molecule of chlorine. The more electrons there are, if you've got a really big molecule, those electrons are very far away from the nuclei, and therefore the molecule is quite polarizable. They can be polarized quite easily. So in the case of large molecules, electrons, far from nucleus, or nuclei I probably should say, plural. So a molecule is more polarizable. Or more, should I say more easily polarized? That's probably easier to say. More easily polarized. Right? So the molecule's more easily polarized the bigger it is. And so, and that increases the strength, number, and the frequency of those temporary dipoles that we get. Right? So, number of electrons, size of molecules. Nothing you didn't know already. But if you've got actually, let's add the size of molecule and size of atoms within it. So if you've got bigger atoms, you've got bigger. So if you had a molecule containing iodine, which is a huge atom with loads of electrons, that's going to be bigger than the same molecule but with chlorine instead. Okay, because there's fewer electrons. Other things. So the length of the chain of maybe a bunch of it's linked to the size of the molecule really. So if you've got, often we'll be talking about hydrocarbon chains here, so the longer the carbon chain, the bigger the molecule. You then get more contact points, a greater surface contact overlap. And I'll draw a picture to show you what I mean by that. So greater surface contact between molecules. And so if I were to draw, I've drawn there a molecule of 1, 2, 3, 4, 5 pentane C5H12. I've drawn it in what we call the skeletal form, which I'll teach you more about later in the year. But that's a pentane molecule. If I have a second pentane molecule, which there'll be London forces between those two molecules, and I'll have a boiling point pentane, I think, of about 60 degrees. I can't remember exactly. But if you take a much longer molecule, that'll be octane with 8 carbons. We've got a longer chain. Can you see there's more points of contact between those two molecules? So the London forces are greater, just as simply more of the molecules are touching each other, can get close to each other. And the closer to oppositely charged things, even though overall they're not charged, but the closer to charged things can get together, as we talked about before, the stronger the attraction between them. So as you go from methane to propane to octane, which is what I've drawn, C8H18, the boiling point goes from it's really significant effect this, so minus 162 to minus 42 degrees C to 125 degrees C. Really significant effects the size of the molecule can have. And that's all to do with number of electrons, greater contact points, 2 factors. Okay? Sure, good idea. Sorry about that. But there's more on top of that too. There's also the shape of molecules. And again, we'll come back to a lot of these ideas when we talk about organic chemistry later in the year. If you've got 2 molecules that are the same size as each other, the same number of atoms, the same atoms even, but you can affect the boiling point by changing the arrangement. So I'm going to go back to, have I got a specific example here? Yeah, I'll go back to pentane as my example. So pentane, this one I drew here, has got a boiling point of 36 degrees C. So I'll draw it again. So if I've got pentane, 2, 3, 4, 1, 2, 3, 4, 5, that's got a boiling point of 36 degrees C. But if and that's C5H12, but if I take a related molecule which has got the same number of atoms of carbon and the same number of atoms of hydrogen, but I arrange it so that we've got what we call a branched structure that's also C5H12. This has got a much lower boiling point. It's 9.5 degrees C. So linear versus branched molecules. And the reason that branched molecules have lower boiling points or linear ones have higher boiling points is to do with packing and how close the molecules can get to each other. I'll do my best to draw that by drawing some squiggly lines. You can see how molecules of pentane can get quite close and you get quite strong interactions between them therefore. But if you try to do the same thing with a branched molecule, they simply just can't get as close to each other. And so the attraction between the molecules is slightly lower. Okay? Same number of electrons, reduces contact area, so lower contact area. I say here molecules closely packed. And they're more loosely packed over here and the contact points go down, right? So that's London forces, quite a lot on that, and there's a bit less on the next force I'm going to talk you through. So I'm going to pause the video for a sec to let you catch up with the notes and then move on. Moving on then, we're going to talk about a very common type of intermolecular force that happens between molecules that have a permanent dipole. You okay? You got everything? Yeah, right. So we're going to talk about something called dipole-dipole forces. And we've spent time in this topic talking about Lewis structures, talking about electronegativity, talking about molecules with polar bonds, and molecules that are polar because they've got polar bonds and are non-symmetrical. A nice simple example of which would be HCl. And I might as well draw it properly as a Lewis structure with the dots around the chlorine. But you should know that chlorine's more electronegative than hydrogen. And so the molecule has got what we call a permanent dipole. Okay, it's a fixed dipole. It's not to do with fleeting movements around the dance floor or whatever it is we were doing before. It's simply always there. And if you've got a neighbouring molecule, that will also have the same polarity as will another neighbouring molecule. And so you might be able to see already that we can build up a network of attraction between these molecules that we call dipole-dipole interactions. So all molecules make London forces, but only polar molecules, molecules with permanent dipoles, can make dipole-dipole interactions. Okay? Unsurprisingly, the more polar the molecule, the stronger the dipole-dipole interactions, but it's quite a subtle effect. But I'll give you an example of the importance of it. So if we were to compare two substances, Br2 versus ICl, what you would do in an exam, ICl is just what we call an interhalogen. It's just an atom of iodine bonded to chlorine. It's exactly the same as bromine, really. They've got very similar formula masses. They've got similar number of electrons. That's got a formula mass of 160. This has got a formula mass of 162. So they're very, very similar in size, those two molecules, and similar in structure, two halogen atoms bonded by one covalent bond. This makes London forces only. This makes London forces and dipole-dipole interactions because it's polar, because chlorine's more electronegative than iodine. And so that means the boiling point of bromine is lower at 59 degrees and ICl is higher because it's not only got the London forces, but it's got the dipole as well. So it increases the boiling point by nearly 40 degrees. It's quite a significant effect, right? So dipole-dipole interactions are not insignificant. And that's all we're going to do on dipole-dipole. Again, I'll just pause the video a sec, give you a chance to catch up, if those of you are behind, and take any questions. So the strongest of the three is what we call hydrogen bonding, which you've heard of in biology. How many of you have heard of hydrogen bonding in biology? Right. Trust me, you don't know what it is. Okay, at this point, you don't know what it is, really. But you might know that it's a relatively strong intermolecular force. You get hydrogen bonding when you've got a hydrogen bond donor and a hydrogen bond acceptor. So when I'm showing you molecules later on, or next time I see you, and asking you whether it's got dipole-dipole interactions or London forces or hydrogen bonding, you've got to think, all right, has it got a hydrogen bond donor? Has it got a hydrogen bond acceptor? So you need to know what those things are. Right, so a hydrogen bond donor is a hydrogen that's attached to, when I say attached to, I mean attached by a covalent bond to either a fluorine or a nitrogen or an oxygen. So NOF. Those are the important elements to remember when talking about hydrogen bonding. And the reason they're important, they're three very, very electronegative elements. So those three elements are super important with hydrogen bonding. Very, very electronegative. The hydrogen bond acceptor will always be present if there's a hydrogen bond donor, but it will be an atom of oxygen or nitrogen or fluorine again. And you'll see shortly when I draw a picture, it will be a lone pair on those that's involved in this interaction. Okay? So we have to have a hydrogen attached to one of those atoms, and one of those atoms needs to be present. Eventually, and if we get time today, we'll learn that you can have hydrogen bonds between molecules that are not the same as each other. One must have a hydrogen bond donor, one must have a hydrogen bond acceptor, but we'll come back to that. So what I'm going to do is draw you a picture of what it looks like and talk about that as I go along. So now, you'll often be asked to draw the hydrogen bonds between molecules and draw them really accurately. And so when I send the slides out to you, actually there's a little slip on the slides I think would lose you a mark on the exam. So this is what you need to be getting down. So I'm going to use water as an example. In fact, what shall I use? Yeah, I'll use water as an example. It's probably the most common one you're going to be asked about. So you all know now that a Lewis structure of water has got lone pairs and has got hydrogens, and we've got that bent structure, and you know hopefully that water's polar and it's got polar bonds within it. And so what you would do, you'd be working out whether water can make hydrogen bonds by checking, first of all, does it have a hydrogen bond donor? Or has it got a hydrogen attached to an oxygen, nitrogen or fluorine? Yes. Has it got a hydrogen bond acceptor? Yes. So water makes hydrogen bonds. In fact, and it becomes important this when we're revising and preparing for tests, hydrogen, because it's got two hydrogens and two lone pairs on oxygen, it can actually make twice as many hydrogen bonds as similar sized molecules. So it's actually got really strong hydrogen bonding and therefore very high boiling points for its size, which we'll come back to. But what you have to do to draw the hydrogen bonding is to draw the neighbouring molecule, and I'm going to draw a water molecule over here, just going to draw it that way around with a lone pair, and we're going to have a lone pair pointing towards that hydrogen. I've not done a very good job of this, I'll explain why in a second. But to get the mark when showing a hydrogen bond, you've got to show that there's an interaction by drawing a dotted line. So there's the hydrogen bonds between the lone pair of the hydrogen bond acceptor, the oxygen, and the hydrogen, which is the hydrogen bond donor. You also need to show that lone pair explicitly, highlighting again, you need to show that lone pair, and it's important to show the dipole here as well, because it's a very strong dipole. It's part of the interaction, it's part of what's going on. So we've got a delta plus, a delta minus. I tend to show the full network of polarities on these as well. So all hydrogen bonding is an interaction between a hydrogen bond donor, which is a hydrogen attached to NOF, and a hydrogen bond acceptor, which is a lone pair on N, O or F. That's all it is. So there's a question there about whether this is the same or similar to a covalent bond. In a sense, it is similar in that there's a lone pair of electrons pushing electron density towards another atom, but this is much longer and weaker than a dative bond, because this hydrogen is not formally accepting that pair of electrons. It's a polar interaction between the polar end of that water molecule and that hydrogen. There is a degree of overlap which is not covered in the scope of the IB, which I'm not going to get into. It's a huge amount of research goes into and has gone into hydrogen bonding. One of the consequences of what you've just asked that I haven't sort of fully answered is something you don't need to know, but it's kind of important for your biology, I would say. So the reason I've drawn this badly is the bond, or the angle between this covalent bond between oxygen and hydrogen, and this dotted line here, is around about 180. So that's a horrible picture, isn't it? It's meant to be linear. It's between about 170 and about 190 degrees, and that's really important in biology because if you imagine that if my arms are, say, one amino acid chain and that folds up into a protein, the shape of that protein relies on hydrogen bonds being directional, in other words, being fixed in direction. And so the interaction between maybe the hydrogen bond donors of this end of the molecule and the hydrogen bond acceptors of this end force it to go into that shape, creating the pocket of a perfect shape, or a protein or a DNA of a certain shape. It relies on hydrogen bonds being directional, and that's partly to do with some stuff that was just mentioned there. But that's not actually required for for IB. You do need to be able to draw this picture. So I'll draw a couple of other examples of this so you can see it. I'll just remind you that these bonds are stronger than dipole-dipole, but not as strong as covalent bonds. So another example might be, I'll do a quite simple example, might be methanol. There's methanol, it's got 2 lone pairs on there, but only 1 hydrogen this time. So there we go, and draw it at 180 this time. A dotted line between the hydrogen, which is a hydrogen bond donor, and the hydrogen bond acceptor of a neighbouring molecule. And so you've got a delta minus there, delta plus there, delta minus there, and a hydrogen bond, which you would label up in an exam. Okay, so these are stronger than dipole-dipole or London forces, but nothing like as strong as covalent bonds. Okay, draw another lone pair on there. When drawing these, make sure the lone pair is pointing towards the hydrogen. Make sure you show the dotted line. Make sure you show the dipoles. I've got 4 minutes, which I want to get this done in, so I'm going to push on. One of the consequences of this, of hydrogen bond, a good example of the evidence of the strength of hydrogen bonds, is when you look at, and this is in one of the question packs I'll give you next week. So if you look at the hydrides of different elements, we can sort of group this. If we do the group 4 hydrides, so that would be methane. You'll see this on the slides as well. SiH4, GeH4, which is germanium hydride, and tin hydride. The molecules get bigger. They're all non-polar. The boiling points get bigger, are higher due to stronger London forces. Okay, so bigger molecules, just like with the halogens. But when you look at the group 5, 6, and 7, we get a slightly different effect. So if we look at group 5, we've got PH3 there, ASH3 there, and SBH3 there. 10 points if you know the element, what the elements are. But the boiling point of NH3, which is the group 5 element at the top of group 5, the boiling point's way higher. So these are increasing in boiling point because they're bigger molecules, increasing in London forces. But NH3 has a higher boiling point than all of them because NH3 can make hydrogen bonds between molecules. So you can see the effect it's having. And that's even more stark. You can do the same thing for the group 7 ones. You see exactly the same thing for group 6. So this is water up here. Water has very strong hydrogen bonds because it's got 2 lone pairs on the oxygen and 2 hydrogens. So if you compare that to H2S, H2Se, and H2Te, tellurium, again, they increase in boiling point because increase London forces. But water's way up here for boiling point at 100 degrees because it's got really strong hydrogen bonds it can make. Okay. What I'm going to do, I'm going to stop the video there.